Okay, so let's go to lecture 9A1, which is about Poynting's theorem. I want to discuss under this the energy flow and storage of energy in in a E and B field or electromagnetic field, as you have been discussing. So let's start with by recalling the idea of the continuity equation. Remember, the continuity equation was a statement of local conservation. Of course, the one that you have done was local conservation of charges. Global conservation of charges is, of course, true, but the statement of continuity of equation is a statement about local conservation of charges. This is a reminder of what something we have already done that sets uh, the form of the kind of equations that you are trying to derive for energy, momentum, and angular momentum, and so on in the field. That's the motive. Now let's look at charge in a volume. That's, of course, Q at any time t is an integral of the charge within the localized charge distribution that we are looking at. So if this is the volume, then Qt, and then that could be could be coming in and going out, which means there is a current at the surface. So current crossing the boundary of the surface of that volume, okay, we can write down as change rate of change of the Q in the volume, and that is the current, the net current. That is, if dq by dt is decreasing, then the net current is going out, minus j dot dA over this area. So we can always write down this dq by dt and bring this under a volume integral by making it partial integration del rho by del t integrated over the volume, and that the right hand side is still the current going through the surface. Now this I can convert, okay, this is a surface integral, the current going to, but we always know the closed surface integral can be converted into a volume integral. That's through the divergence theorem. So the right hand side now I convert into a volume integral, which is minus divergence of j d tau. But this equality is over, is true for any volume, and if that is true for arbitrary volume, and hence this is true for, if it is true for arbitrary volume, then the integrand must be also be equal, and so true for arbitrary volume, and hence the integrand del rho by del t must be equal to minus of divergence of j. You remember this, we did this idea proved or tried to make you understand at the start of magnetostatics, because for magnetostatics divergence of j was 0 or del rho by del t was 0. I'm just recalling that. So local conservation of charge takes this mathematical form. This is not an independent law. It's only a constraint of the type of sources that you can put in the Maxwell's equations. You remember that in Maxwell's equations, the rho and j, okay, are the sources. Okay, and so they must satisfy this equation for Maxwell's equation. So it's a constraint, and it can actually be derived. So most local conservation statements would have this form. For example, energy, momentum, even angular momentum, and so on and so forth. So that's the motive, and our special emphasis would be on continuity equation for energy in the electromagnetic field. So N is a continuity equation for energy density. Okay, that's just like it was therein for charge density, this is for energy density. So we know the electrical energy stored in a electromagnetic field, that is all space epsilon by 2 e squared theta. This we have done many problems on. We have also magnetic fields also stores energy in all space, and that is 1 by 2 mu naught b squared theta. So we have a electromagnetic field, and of course part of it is in electrical form, part of it is in magnetic form. So at any time, I can then write down the electromagnetic energy per unit volume. These are all space, right? Per unit volume, this will be just the integral. Okay. So that we define it as U, small u, and sometimes I'll also write it as UEM, okay, where there needs to differentiate between different type of symbols, and so U is half epsilon E square coming from electrical, and 1 by 2 mu naught B square coming from magnetic. This is per unit volume. That's important to look at. Now recall again the form of the continuity equation for charge and current, that's del rho by del t is minus divergence of J. This is the rate of change of charge density, and on the right side is the space derivative or the divergence of charge flux. Okay. So our task is to now write down a continuity equation of this form, okay, where instead of charge density, we have the energy density. That is the task. So that we can write down del U by del T is minus divergence of a quantity which you can call as energy flux. This was divergence of charge flux. This would be energy flux. Now this is a new character. Okay. So this is of course rate of change of energy density stored in the electromagnetic field, and this will be the divergence of energy flux. And this S is a vector, okay, is the new character that we'll be interested in this brief lecture. Now, Poynting's theorem is a theorem about work energy in electrodynamics, just like we had work energy theorem in mechanics. So this is the work energy theorem for electrodynamics. Let's consider some charge and current configuration at time t, and some charge moves within the next tt. Okay. So then we want to find out what is the work done on charge q in that current and charge configuration which stores E and B energy. That's the work done. Work done, of course, F dot dl, and that's the Lorentz force dot dl. I can write down in terms of V dt. And hence, you know, this doesn't do any work. So it will be only the electrical part, QE V dt, that will be the F dot dl. Assuming, just for simplicity, only one type of charge, of course, one can do it for boards, but the proof is exactly similar. So what I do is I replace this Q by rho d tau so that I can go and do an integral form, and this V in terms of J. Rho V we know is J. So I can write down this, the rate at which work is done on all charges in the volume, that will be dW by dt within the volume, E coming from here, okay, E d tau, and V dt, okay, J. Okay, so E dot J d tau is the work done, rate of work done on this charge and current configuration. Simply E dot J over the integrated over the volume d tau. Now this E dot J can be considered as the work done per unit time per unit volume, that is power delivered per unit volume. Now in terms of field variables alone, if I want to write this down, then E dot J I can write down in terms of E and replace J by del cross B by mu naught, and of course epsilon naught E del E del T. This is the displacement current, and this is the real current, del cross B by mu naught E dot J, right? So there are two terms coming from displacement current and real current. So now I can see that this quantity, that's the usual trick, okay? So that find a product rule so that you can replace this by, our aim is to make it such that it will be divergence of E cross B. So divergence of E cross B is of course B dot curl of E minus E dot curl of B. And this is the term that appears here. So I can express this term in terms of divergence of E cross B and this. So I bring this to the left, okay? And of course, I know that del cross E, I can replace this also by Faraday's law minus del B by del T. Then I rework, I bring this to the left and take this to the right, becomes minus, and replace del cross E by del B by del T. So this is minus del B by del T, divergence of E cross B. So that I can replace here E dot del cross B by these two terms. Okay. Remember, there's already this term which is E dot dou E by dt, and this is now going to become B dot del B by del T. So these two terms I can collect together and make the energy, and this term will be uh, in terms of divergence of E cross B. So, and I can always express B dot del B by del T as half del B square by del T. Similarly, even this term can be expressed as E dot del E by del T as half del E square by del T. So this term and out of this term out of this expression and this term out of this expression can be taken together and put back in E dot J. So, and I take all del by del T common. So half del is epsilon naught E square plus B square by mu naught. And this term sticks out as divergence of E cross B. This is the kind of thing that we have done many times over in deriving things, right? And you can probably judge the goal that once you get divergence, you can convert it into a surface integral. So let's put back this EJ here in this equation, okay? Then it becomes d, the rate of work done is minus d by dt of this quantity, okay? And 1 by mu naught surface integral, okay, of E cross B dot dA. Now this we already know what this quantity is. This is U. So this is the rate of change of total stored energy in the field per unit volume of current. This total energy is integrated over volume. This integrand was per unit volume. So this is the rate of change of total stored energy in the field. And this is the energy going out through a surface S that bounds this volume. Okay. So rate of energy crossing the boundary surface, E cross B. So this is, what is the units of them? This is S some quantity dot dA, and this must be flux, because the total energy comes out of the flux integrated over the area with dotted dA, and hence this quantity is an energy flux. So the work done by electromagnetic force is the decrease, the first term signifies the decrease in stored energy, minus the energy outflow through the surface bounding that volume. This is the statement of Poynting's theorem, okay, relating the work with the loss of energy stored and the energy flow out. So that is exactly like, as I said, work energy theorem of electrodynamics. So this is the equation form, mathematical equation form, and this is the conceptual word form of Poynting's theorem. Simple enough. Let's take it forward. So the vector that I was trying to define is called the Poynting vector in that equation. So dw by dt, let me write down it again. This was u integrated over volume d by dt, and this is a flux going, energy flux going throughout the surface of this bounding volume. That was Poynting's theorem. Now this 1 by mu naught E cross B I can define as the character that I introduced to you, that is energy flux called the Poynting vector. So this is defined as 1 by mu naught E cross B. Now let's write it down. This is the Poynting vector, and what is it in terms of work? Energy transported by the field per unit area. That's the really the definition of a flux of a quantity. Now, Poynting theorem can be now written more compactly once I've defined this. I've already defined this integrand as u, so I can write down as dw by dt is minus d by dt u. This is the energy density, and this is the flux, energy flux, in terms of energy density and energy flux. That's the compact expression for the Poynting theorem. In fact, this is the form that you'll probably remember. Uh, Suppose no work is done, that is dw by dt is 0, then I can take this term to my left. Okay, so and I can take the explicit time derivative into the volume integral. So the left hand side becomes, so this is taken to the left side, and that's why it's positive. And then I take del u by del t d tau, and this is true for arbitrary volume. Okay, which is volume and the surface. Now this surface integral can be again be converted into a volume integral by our old trick, take the divergence of s d tau. So now this is the volume integral, this is the volume integral, and is for arbitrary volume, and hence the integrand must be equal. Exactly the kind of reasoning that we did for charge and current density. So therefore, I can write down as del u by del t minus, this was our aim to prove. So this is the continuity equation for energy density. So for, you could say for energy, just like it was continuity equation for charge, this is continuity equation for energy. And which is, to remind you again, is the local conservation of electromagnetic energy. But let's take a note that we are talking about local conservation of electromagnetic energy. That doesn't mean electromagnetic energy is conserved within the field, because the energy conservation, we always know about the system. So if there is an electromagnetic field interacting with the system, which is mechanical or whatever, or even heat, then there would be changing of one energy to the other. This is only a statement about continuity of electromagnetic energy. This is not about that electromagnetic energy is conserved. Of course not. Okay, so let's take an example, and this is one of the most famous examples which demonstrates the Poynting vector, the use of the Poynting vector. So we have seen a microscopic viewpoint of origin of Joule heating earlier by using the Drude model, right? That's the in fact purpose was so that I can talk about it here. Now let's take a conductor, okay, a chunk of conductor cylinder of radius A and length L, okay, and a current flowing I and length L. I is flowing in this direction. Now, so assuming that there is a potential difference between the two faces, let that be V, then what is the E is, let's assume that E is uniform. There are more complexities in talking about the electric field in a current carrying conductor, because there can be some surface charges. But let's keep it simple. For simplicity, let's use that E is uniform, as I had shown in my introductory lecture last week. E is uniform and parallel to the where. All right. And so, and on the surface, for example, it would be the component that is parallel to the where, the axis of the where would be E. And let's say that is what we're considering. So that will be, of course, if the voltage drop across this faces is V and the distance is L, then uniform E is equal to V by L. So that is my E. Now, the magnetic field, then, the current is flowing in this direction. So the magnetic field is circumferential. Okay. And at the surface, let's say at this point in the surface, it will be pointing in this direction, in the phi direction. Correct? This is if it is in the k hat direction or z hat direction, this is in the phi direction. And what is its value? Of course, the enclosed current mu naught I by 2 pi I d. That's the magnitude. So now we know the definition of the flux, energy flux, and that is 1 by mu naught E cross B. We know E, we know magnitude, we know direction, we know the magnitude and the direction of the B field, and hence I can calculate the energy flux Poynting vector S. Let's do that. So first, what is the direction? E cross B, K cross phi, and that will be minus S hat direction coming in, right? Uh, which means energy flux is coming into this conductor wire, all right? And let's calculate the magnitude, okay, of the flux. So magnitude of Poynting vector then is, we already know E and B, they're perpendicular, 1 by mu naught, V by L from here, and mu naught I 2 pi A from here. Mu naught cancels, and so this will be equal to VI by 2 pi AL. Now that's an energy flux. We know the direction and we know the magnitude of the vector. Now we can calculate, just to write it down, that the pointing, this vector is pointing radially inward into the conductor. Now let's calculate then the total energy crossing this surface for this whole volume that we are under our consideration. That will be S dot dA, and S dot dA is S hat. dA is also, this is minus S hat. dA would be S pulse, okay, also in the same direction for the flux coming in. So S 2 pi AL, okay, and so 2 pi AL and 2 pi AL cancels, so you are left with V into I. Okay, so that is nothing but the power that is, delivered by the current in form of heat. This is the Joule heating. So is the power dissipated due to Joule heating in this portion of the conductor flowing in. And now we're showing what this equation shows, that where is this power coming from? This is coming from into the conductor through the surface of the conductor from the field B and E. Okay, so that is Poynting theorem is telling you that the heat generated is actually the expense of energy stored in E and B field. That's the whole purpose. But this is the viewpoint from the point of fields, E and B fields. But we have seen, we have already proved that Joule heating is sigma square E, and that is also VI, and that is from the microscopic point of view. So this is the consistency between the um, microscopic view, in which where was the heating energy lost was coming from was because of the electrons undergoing collisions, and every time they undergo collision they lose all the momentum they had gathered before the collision, and that energy is lost, and that we showed was the heating. That is the microscopic point of view. The macroscopically we can consistently obtain from E and B fields this way. That's the typical use of the how the power flows in a E and B field. This is demonstration of. Now, similarly, I've talked about so far conservation of energy, but similarly, we can talk of conservation of momentum and angular momentum. This I will not derive explicitly. You are not required to derive. But since we now know the form, I can take advantage of it in just stating the result and using it later. We know the Maxwell's equations are consistent with conservation laws of classical mechanics, taking, of course, fields into account, and also consistent with special theory of relativity. In fact, special theory of relativity was born out of a question in electromagnetic theory in 1905 by Einstein. That was electrodynamics of moving bodies and apparent asymmetry of Faraday's law. Okay, I'll probably have time to talk about it towards the end of the course. Um, a little bit of special theory of relativity in relation to electrodynamics. Without proving, let me state, the local conservation of field momentum. Okay, is the same form as my continuity equation. So this is dp mechanical momentum by dp by dt. There is nothing but the force. So the force, where does it come from? Right? In terms of field terms, it is a rate of change of s d tau. S is a Poynting vector, something going out, and a new character again, T dot dA. Now let me say what is T. T is stress tensor. Okay, so this is a term which is momentum per unit time flowing through the surface. Okay, if we're considering the charge and current configuration, then into that configuration there is momentum flowing in from the field. Okay, and there is energy flux that is going out. It's integration with in volume with a rate of change with epsilon mu naught. Okay, so let's first look at what is this T. I had put double arrowed head. It's a tensor. Okay, so it's a tensor which is called stress tensor. And why is it a tensor? It's acting on the surface of the charge configuration because Tij, stress acting in the ith direction on an area element oriented in the jth direction. That is why it's a tensor. For example, I could be x, j could be x, it will be txx. I could be y, j could be x. That is stress acting in x direction, but the area element is pointing in the y direction. Okay, so that would be Tij. I have not derived it, but you can understand there is the surface on the, this is about the momentum per unit time per unit area. Okay, that's on the surface. And then what is this quantity? This quantity you can recognize as if there's a momentum stored in the fields per unit time. This is momentum flowing in, and this is rate of change of momentum. And that is what the two sources of force, one is because of stress on the surface and the rate of change of momentum. Momentum stored in the fields per unit time that is being spent in producing this force. Okay, so in that case, I can define the momentum in the field, momentum stored in the field, epsilon naught mu naught s d tau. Okay, so that is momentum stored in the field. And I can talk about momentum density, which is more important. Okay, that is in Griffith's notation, it is G epsilon naught mu naught S. Okay, that is this over volume. So if I take momentum per unit volume, then this becomes epsilon naught mu naught S, which is epsilon naught E cross B. Okay, because S is 1 by mu naught E cross B, so mu naught cancels. So G, that is momentum density, was epsilon naught E cross B. Simple enough. So if momentum density is there, can angular momentum be far away? So it will be angular momentum density. So angular momentum density would be R cross G, of course. Okay, so that is, let's Griffith's relation L, that is angular momentum density, small l, which is momentum density, remember. Okay, so that is R cross G is epsilon naught R cross E cross B. Now, so that's a surprise, that the E and B field that we have so diligently worked up in making this nice theoretical framework that now includes, okay, momentum and angular momentum. E and B fields, of course, have no material mass or actual material, but they also store momentum and angular momentum, and it can flow in and flow out like any other quantity. And that's, looks a surprise, but we have seen at least two examples of angular momentum. For example, you remember while discussing Faraday's law, we had talked about an example in which the center of the wheel was a magnetic field, and the wheel was outside. And when I switched off the magnetic field, then electric field was induced. And if it is free to move, then this wheel will now start rotating. Now, which means it picks up angular momentum. Now, where does that wheel get angular momentum from? It gets it from the E and B field. Or a problem that you did in homework 9, in which we set a cylinder rotating to its final velocity, final angular velocity omega f, okay, against working against the backward EMF. So where that angular momentum came from? It all came from the E and B field. That's a surprise, but the conservation laws are preserved. Newton's third law and everything that we know, all the principles we know of conservation and classical mechanics are preserved if we take the field into account. So in summary, I can say that EM fields store energy and momentum and angular momentum, and these are conservation principles, and laws of Newtonian mechanics are all obeyed, as you would expect a valid physics to obey. Now, E and B fields have now taken on a life of their own, storing energy, momentum, and angular momentum. That was the message of this brief lecture. Now, local conservation of any of these quantities are expressed in equations of the form of the continuity equation. Now, two things that I have not done, let me list down here. What I am yet to do, that is, I am postponing to the end of the next chapter probably, is the potential formulation. How do we now express A and V consistently once we have admitted that things can change with time? In electrostatics, we had defined V because it was electrostatic field was conservative, and hence we could define the electrostatic potential. In magnetostatics, we had considered that divergence of J is zero, and hence del rho by del T is zero, and because of that I could define the A vector or the vector potential vector. Now that we have admitted that E can be changing with time, and B could be changing with time, rate of change of B determining part of E, and rate of change of E determining B, do those old concepts of electrostatic potential and vector potential make sense? Okay, after we have gotten the full Maxwell's equations. That's a question that we'll take it up after we have done through electromagnetic waves. I don't know if I'll have time, but it'll also it's electromagnetic fields in terms of relativity. How about the laws of Maxwell's equations in a moving frame? Can E and B transform into each other? There is a suggestion, because the magnetic force is V cross B. Suppose I am now moving with the charge at a velocity v, then v cross b would cancel, and it will look like as if, but there must be a force. So that force would look like as if it is electric force. So what is the transformation between E and B field if I am in a frame, moving frame with a constant velocity? That's a question that I don't still know whether we'll have time enough to discuss, but I will try and do that. So with that, I close this lecture, and we'll take up equations, the wave and in the next one. Thank you.